Sorry about the minor delay. Okay, welcome to lecture 2. Today we'll be looking at two learning algorithms, the Perceptron learning algorithm and stochastic gradient descent. First, just a recap of some of the things that we saw in lecture 1. We saw the basic recipe for supervised machine learning. And just to remind you, although you're already familiar with this, the basic recipe consists of 4 components. First, we need a supervised training set, which includes both the raw inputs, which I know by x, with some feature representation of it, and a supervised target. In this case, in this example, it's binary, y is +1 or -1. Then we need a definition of a model class. So what is the class of models that we will be learning over? In the simplest case, we'll use linear models, and we'll keep with linear models this week and next week, and we'll move on to nonlinear models in week 3. The loss function is also something that we need to specify. It characterizes the mismatch between the supervised target and the prediction that our model makes. So in this simple example, it's squared loss, which means that if the true target is A and our model predicts B, then the penalty we pay is A minus B squared. And finally, all these things get put together into a learning objective, which simply says, given the definition of a model class, given a training set, and given the definition of a loss function, I want to find the model within this model class that minimizes this loss function summed over all the examples in the training set. And that's essentially what much of machine learning is. Indeed, all the popular machine learning approaches that you hear about and that get used in industry certainly fit within this paradigm. Although, of course, the model class may be much more complicated, or the Ys, the supervised targets, may be much more complicated. For example, if we're doing machine translation, which translates from, let's say, English to French, then X is an English sentence and Y is actually a French sentence. But this is it all follows sort of this same basic setup. Okay, we also talked about the Biasvariance tradeoff. And the basic idea behind the Biasvariance tradeoff is that when we are choosing our model class, in this simple case, it's univariate regression with either a linear model class, a quadratic model class, or a cubic model class. And when we're choosing which model class to use, we have to think about the Biasvariance tradeoff. And what this is related to is the concept of overfitting. If our model class has a lot of variance for the training data and the training task that we are asking it to do, then we might suspect that it is overfitting to a small training set. If the model class has high bias, which means that even if you give it infinite training data, it will still have a lot of error. That simply means that it cannot fit the model, the data well. And the goal of looking at the Biasvariance tradeoff is, well, we actually want to choose a model class that optimizes the Biasvariance tradeoff. The cubic function class can fit the data really well in this example, but with only a few training examples, it tends to overfit to the idiosyncrasies of the data points that you sampled from the true distribution. And the linear function class is too simple. Even if you give it infinite data, it'll still have high error. And that's due to the bias in the model class. And in this particular example, where we're selecting 7 training data points and training off of that, the quadratic function class, or model class, has the best compromise. And so here is the more or less complete pipeline. We specify our training data, we choose a model class or a family of model classes or a collection of model classes, specify a loss function. We use some sort of validation mechanism to select the model class, for example, 5-fold cross-validation. And then we choose the function that we think has the best compromise of bias and variance, and then we deploy that, and that's how we get an effective machine learning algorithm in practice. Any questions on that? Just review from last lecture. Okay, so today we'll be looking at 2 basic machine learning algorithms, the Perceptron algorithm and stochastic gradient descent. The Perceptron algorithm is just, for the purposes of, I guess, modern practice, the Perceptron algorithm is more just a conceptual algorithm at this point for most practical use cases, but it's an important one and it is a good one to sort of get us thinking in the mode of a learning algorithm. Stochastic gradient descent and its derivatives are the most popular learning algorithms in practice these days. In fact, if you ever use something like TensorFlow or PyTorch, which, by the way, you will in week 4 in this class, all the learning algorithms are using a variant of stochastic gradient descent. Okay, so let's start with the Perceptron algorithm. It is arguably, well, it is certainly one of the earliest learning algorithms, arguably the earliest, although the origins of machine learning are sort of murky. It's still a great algorithm for many applications in terms of, at least in terms of the simpler ones. It's fast, it has a very clean analysis, and in many ways the Perceptron was the precursor to artificial neural nets and deep learning that we use a lot these days. What you see in the picture right there is Frank Rosenblatt, who is the inventor of the Perceptron, implementing the Perceptron algorithm on the Mark I machine, which used actual wires instead of bits to do programming. I think your phone is much more powerful than that computer right there. Okay, so let's just dive right into the learning algorithm. And we're going to use a linear model. So the model class is linear, so we should be quite familiar with the model class at this point. And so let's step through the perceptual learning algorithm. And this is the case for classification. So we're going to take the sign of the raw score of the linear scoring function, and we'll predict positive class if the sign is positive, and we'll predict negative class if the sign is negative. So we initialize the parameters of our functions to the origin. This is not strictly necessary, but it makes the analysis cleaner. And then we iterate for a number of time steps. So t is the index of the number of time steps of learning. And at every iteration, we receive an example from the training set. For example, you could just randomize your training set and include them in some random order. It doesn't actually have to be random, it could be arbitrary. And if the current prediction of our function equals y, and I guess this should also depend on b, but suppress that for brevity. Then we don't do anything. Our new function parameters are the same as before. Otherwise, we do an update, and we do an update in the following form. The model parameters are shifted towards the direction that would make the prediction the way we want. So, for example, if y was positive, this would make the dot product of w and x more positive. So, if this was below the threshold, it would make it above the threshold. And if y was positive or negative, if y was negative, we would make the dot product more negative. And y is just an offset on b. So if we made a misprediction, then if y was positive, we would lower the threshold, make it easier for the sign to be positive. And if y was negative, we would raise the threshold, make it easier for the sign to be negative. That's the basic idea. And we'll walk through some examples of how this algorithm behaves in practice in a few slides. So as an aside, and this is something that we'll touch on more next week, the way we can think about the perception algorithm and other machine learning algorithms can be related to a concept known as the hyperplane distance. So a line is a one-dimensional hyperplane. A plane is a two-dimensional hyperplane. And a hyperplane, more generically, is just the same concept in many dimensions. And it's defined by w and a v. And in this particular case, the w is the tangent normal for of the line. The unnormalized tangent to the hyperplane, and the v is the offset from the origin. So if b was 0, this hyperplane would cross the origin. And for those of you who know about, if you remember from geometry, if w was normalized to have unit norm 1 to have unit norm, then it would be the tangent normal. But this is just the unnormalized case. Okay, so that's the formula for distance to hyperplanes. For any point x, its distance to this hyperplane is defined by this formula. This should be reviewed for everyone here. We can also think about the sine distance, right? So is it you know, if this is the normal of the hyperplane, then this is the positive face, and this is the negative face of the hyperplane, let's say. And so we can talk about sine distance. If this number is 0, it's exactly on the hyperplane. If it's a large positive number, it's on this side of the hyperplane. If it's a large negative number, it's on this side of the hyperplane. And a linear model, the scoring function of a linear model, right? When a linear model scores an example, it's actually, the raw score is actually just the unnormalized sine distance from the hyperplane. So in some sense, there's an equivalence, or rather a geometric interpretation of a linear function, of a linear model, which is that it is essentially a unnormalized hyperplane representation in some geometry space. And when we think about the raw score of that linear scoring function is geometrically equivalent to the unnormalized sine distance to this hyperplane. Now, of course, this hyperplane can be very high dimensional. You know, if D was 10,000 or a million, this is it's hard to think of, visually think about what's happening. And so it can be a very high dimensional concept in practice. Okay, now let's walk through what the perceptron algorithm is doing. And you know, obviously for visualization purposes, everything's in 2D. And we're going to ignore the bias term B just for simplicity of the illustration. So everything's going to be around the origin. So here's my training set with positive and negative examples. And initially, my model is basically at the origin. It's nothing. And so we're going to pick an arbitrary training example. Let's pick this one. By default, the first one is always being misclassified because the sign of 0 is 0, which is unequal to 1 or negative 1. So by definition, the first example is always misclassified. We're going to move the tangent vector, W, in the direction of this data point because it's a positive data point. And now here's our new hyperplane. So the dashed blue line is our hyperplane, and we moved in the direction of the normal, the W is the normal, which is the solid blue arrow. So this is our model. And again, we're just forcing B to be 0 for simplicity. So everything's going to be rotating around the origin. In practice, of course, that's not the case. Okay, now let's pick another arbitrary data point. Let's pick this one. Okay, it's on the positive face of this hyperplane, which means the sign distance is positive, which means since this is a positive label, excuse me, positive example, we do nothing. The perceptron algorithm doesn't do any update if the classification was correct. So we do nothing. Let's pick another example. This example is also on the positive face of the hyperplane. The unnormalized sign distance is positive, but it's a negative example, so the actual classification is incorrect. And so we're going to make an update. And since this is a negative example, we make an update in the opposite direction of the feature representation x of this example. So we're going to move in the opposite direction. So that's our update. And this is our new model. So this is our new model. The dashed line is the hyperplane, and the W is the tangent unnormalized tangent vector, which is the solid blue arrow. Let's pick another example. It's correct. This example is on the negative face of the hyperplane. It's a negative example, so the signs match, so we don't do anything. This one's also correct. It's on the positive side, the signs match. This one's misclassified. It's close, but it is misclassified. So we're going to move in the positive direction of this x. That's our update. And now, it's easy to check that you will never make any more mistakes in this training set. You can loop through it over and over again. You'll never make another update because every example has been classified correctly. Okay, let's start again. Let's pick a different example as an initial example. This one. By definition, the W is at the origin in the beginning, so it's going to misclassify always in the beginning. This is a negative example, so we're going to move in the opposite direction of this example. And that's our new updated model. Let's pick another example. This guy, he's correct. So we move on. Correct. Move on. You know, I had a lot of fun making these slides. So this guy is misclassified because it's on the positive face of this hyperplane, but it's a negative example. So we're going to make an update. It's a negative example, so we're going to make an update in the negative direction of this example. That's our update. Correct. Correct. Misclassified. Make a positive update towards that direction. Correct. Misclassified here. Do a negative update. Misclassified. Negative update. Still misclassified. Same example, still misclassified. Do a negative update. Or excuse me, positive update. Sorry. There we go. Now we're done again. At this point, it's easy to check. If you write a for loop over all the examples, no more. You will not do any more updates. Okay, so that's pictorially what the perceptron algorithm is doing. Of course, in practice, there's also a bias offset term B, and in practice, of course, it's much higher dimensional. But that's the basic idea. Okay, so let's recap the perceptron algorithm. Now that you've seen it in action, we can look at the pseudocode again and try to sort of digest both the example and the pseudocode. And you know, we see that we start with the origin. If we go loop through the training set in some order, if we make the correct update, we don't do anything. Or excuse me, we make the correct prediction, we don't do anything. And if we don't make the correct prediction, we do an update. And this is the most important line in the code, of course, the update rule. And the update rule says, I want to move W in the direction of X, either positively or negatively, depending on the label of that example, and same with the bias term. And that's the entire perceptron algorithm. So we can compare the two models that we learned. So this is the final two models from the previous two examples with two different orderings over the training examples. And this is what they look like. They're pretty similar. And in fact, for data sets that look like this, you can actually prove that all of the hyperplanes will have some similarity, because there's only so many different types of hyperplanes that get zero error on this training set. So now we're going to talk about a concept called linearly separable. A training set is a binary training set, let's say, for simplicity, is linearly separable if there exists a hyperplane that separates the positive and negative examples, such as this one. Furthermore, there's a concept known as a margin. What a margin is okay, there's the margin of a hyperplane, and then there's the best possible margin of over all possible hyperplanes. So the margin of a hyperplane is simply the closest example to the hyperplane. And here we're only going to consider hyperplanes that actually separate the data, positive and negative. The max margin over all possible such hyperplanes simply just takes the maximum over all possible hyperplanes and computes the margin. And this is simply the definition of the closest point to the hyperplane. Any questions on that so far, or anything else? Okay. So a classification problem is linearly separable if there exists a hyperplane. Again, I'm not mentioning the B just for simplicity. Nothing changes with the bias term. If there exists a hyperplane with perfect classification accuracy, the classification problem is separable with a margin gamma, which is the maximum, which is the hyperplane equal to the margin of the best possible hyperplane that separates the data. And more formally, a problem is linearly separable if this margin is strictly greater than 0. Okay, so it turns out that the perceptron algorithm for a linearly separable problem is always guaranteed to stop. There will always come a point where it will make no more mistakes and therefore make no more updates. and therefore, basically, you can terminate the algorithm. Number of updates it makes is equal to the number of mistakes it makes while it loops through the training data. And so one question one can ask is, well, how many mistakes does it make, or how many updates does it need to make before it terminates? And you can prove that the number of mistakes is upper bounded by the following quantity. So R is the radius of the feature space. You can also do the diameter if you add some coefficients, like divide by 4 or something like that. And gamma here is the margin. So what this basically says is, and notice that this is a ratio. So if I make all the, if I blow up all the training sets, if I blow up the training set, make all the features bigger, the margin correspondingly increases, right? So I could just think of R as 1 without loss of generality, and this is basically saying that as the positive and negative examples get closer together, even though the problem is separable, the closer they are, I require quadratically more updates to get to a mistake-free model. Yes.
Should the radius depend on more than one space? If you have some type.
Yeah, I'm assuming things are centered around 0. So this is a simplified result. I'm assuming that data points are centered around 0. If not, you can reshift. So that's where the B is. If there's a close relationship between the B, the bias term, and the center of mass of the data points. So I'm assuming that it's centered at 0. If not, you can always shift everything. So if you center it at 0, then you do some tricks. You can ignore the B in the analysis and everything. But you're absolutely right. So let's assume the data points are all centered. The data mass is centered around the origin. If you want the full analysis where you don't assume all that, and you could look at the paper. I'm just giving you a simplified result. Okay. By the way, this holds for any ordering over the training examples. So I could loop them in arbitrary order. Yes? Yes, it's in the paper. There are many proofs. It's a classic result. It's been there are multiple ways to prove it, in fact. It's one of the beautiful things about this algorithm, and in fact, you can build on this proof to look at more complicated prediction settings. It's a pretty nice result. Of course, in the real world, many problems are not linearly separable. And so the perceptron algorithm, in that case, may never converge. It might loop around forever, because there will always be at least one example where it's making a mistake. That's the consequence of a data set not being linearly separable. So it'll never stop making updates. So what do? Well, the standard thing that people do is they use a validation set. So what does that mean? Well, the one thing is to do what's called early stopping via validation. Early stopping is a very popular thing that people do in machine learning in practice. So we run the perceptron algorithm on a training set. We have a separate validation set. We evaluate the model that we're training on the training set on this validation set. And then when the validation accuracy stops improving, we stop. That's what early stopping means. And you could do this for a variety of machine learning algorithms, Perceptron being one of them. And so this is a way of saying, okay, this data set is not linearly separable. That's fine. We'll just run the perceptron algorithm until the error on the validation set doesn't decrease anymore, and then we'll call it a day. Yes?
Could you run into issues where you reach a local minima and don't actually find the best separation?
Perceptrons. I don't think that happens for perceptrons. It certainly does for deep neural nets. Yeah, so then you would do multiple restarts. So
Okay.
I'm not going to talk about that in this lecture, but then you would do multiple restarts to pick the best one. That's what people do in practice with deep neural nets. Okay, so I want to briefly, and this is just an aside, it's not the main point of the class, but I want to briefly touch on the difference between online learning and batch learning. In online learning, and both can be supervised or unsupervised or whatever. This is an orthogonal notion called, this is an orthogonal dichotomy on learning versus batch or versus supervised or unsupervised. Online learning is the setting where you receive a stream of data. In the supervised case, XY pairs. And the learning algorithm in an online learning setting makes small incremental updates, typically, to the model as it's receiving this stream of data. So the Perceptron learning algorithm is an instance of online learning. It takes as input a stream of data, and it makes small updates, or relatively small updates, until it decides to stop for whatever stopping condition you're using. In batch learning, all the data is given to you up front. So we're given a data set. And we then do something on this data set to do learning. Many of the popular learning algorithms in the batch setting are in fact online learning algorithms. You just simply write a for loop that loops over your training data and then feed it into an online learning algorithm. There are many reasons for this. Online learning is often an easier setting to analyze, and it's often convenient because you're only processing a few data points at a time, and that's very convenient in many cases. But online learning can be applied more generically. So for example, if I'm training my model on the Twitter data stream, that is a strictly online learning setting. There is no batch setting that's surrounding it. So even though in the batch setting, you typically convert it to an online learning problem by just writing a for loop wrapper around the training set, online learning can be used in cases where batch learning is not even applicable. It's not the focus of the course, but just thought I'd sort of illustrate that dichotomy. Okay, so just to recap, we looked at the Perceptron algorithm. It's one of the first machine learning algorithms. Some might say it's the first. Some benefits: it's simple, fast, very clean analysis. It's a very beautiful algorithm in many ways. Some drawbacks: it may not converge to a very good model. But one of the things that's kind of weird about the Perceptron algorithm is that, well, from everything that we learned in the first lecture, what is it doing? In the first lecture, we set up a learning objective. We want an algorithm that minimizes this objective, this loss function over the training set. I just gave you an algorithm. I did not tell you anything about what objective it is actually optimizing. So from that sense, the way we even think about the concept seems to be at odds with how we think about the concept of machine learning in the first lecture. And I'll get to this at the end of this lecture. Any questions before I move on to stochastic gradient descent? All right, stochastic gradient descent. So I'm going to come back to optimizing objective functions. So this is our setup, and at the end of the day, we have this learning objective that we want to optimize. And we can find a parameterization of our function class that minimizes the objective that we can at least subject to overfitting, at least ignoring overfitting concerns. We've learned something interesting about this data set. Okay, so typically this requires some sort of optimization algorithm, the simplest of which is gradient descent. For those of you, for that thinking 156, a gradient is simply just the multivariable derivative of this objective function. So you take the derivative of this with respect to, let's say, the w vector, and that's the gradient with respect to w of this objective function. In this lecture, we will stick with squared loss as the loss functions because it's the easiest loss function to sort of work through the math. Everything I'll describe generalizes to other loss functions without any loss of generality from this lecture. You just sort of apply the chain. So here's the review of how we derive the gradient of the squared loss. So this is the gradient of the loss function with respect to the w vector. So this is just the definition of the loss function. So we replace this with the definition of the loss function, which sums over all the training examples. By linearity of differentiation, we can move the gradient operator inside the sum. We use the definition of squared loss and apply the chain rule. So the definition of the gradient of a minus b squared is 2a minus b. So it's this guy. And then we apply the chain rule, so we apply the gradient operator on the model class which has the w as a parameter of it. And then we use the definition of a linear function class. So f of x equals w transpose x minus b, and take the gradient of this guy, and we just get x. So this is the gradient of our learning objective with respect to the w vector. Should be reviewed for almost everyone here. Okay, and gradient descent basically says, okay, let's initialize again at the origin. It doesn't have to be, but most people initialize at the origin. When we move on to deep learning, we won't be initializing at the origin, and I'll get to that we'll get to that in week 4 when we move to deep learning. But for now, let's initialize at the origin. So gradient descent is an iterative algorithm. So let t be the index of the iterations or time steps, and we keep, at every iteration we have an intermediate solution, and we simply take a direction in the we simply take a direction in the negative direction of the gradient. So remember, the gradient tells us what is the direction of steepest positive slope of this objective function with respect to the parameters, in this case w. Since we want to minimize this objective function, we simply go in the negative direction of that. So we do an update step in the negative direction of that. And that's gradient descent. And as eta term is just the step size. So if eta is really small, we make a small update. If eta is large, we make a large update. Okay, so we can sort of start thinking about this concept in a simple example. So here's a simple example. It's a one-dimensional regression problem. So this is the actual gradient. The x is just a unit. The x is always just 1 for simplicity. So this is the loss function. So when w equals 1, the loss is 0, and when w, this is a unit varied w. It's not a vector. It's just for simplicity of the example. And when w deviates from 1, the loss increases quadratically. Okay. And so the gradient at this w equals 0, this gradient, is simply this slope, this purple line. Okay. It's the tangent to the curve at that point. And it's pointed in negative, so it's pointed in this direction because that's the direction of steepest ascent of this loss function. So we're going to move, in the opposite direction. So we're going to move, in the your right direction. That's the opposite of the gradient, and update w. And our step size, let's say the step size is 1. Okay, so 8 equals 1. So we're going to go from w equals 0 to so 2 minus negative 2 times 1 minus 0 is just minus 2. So we're going to move w equals w minus 2. W equals w plus 2. So w equals 2. Okay, now we're over here. Compute the gradient again. And the gradient is, so w equals 2. So 1 minus 2 is negative 1. Negative 2 times negative 1 is 2. So w equals 2. So moving in this direction, this is the steepest descent, that's the slope. So we're going to move in the opposite direction of that with step size 1. And we're back over here at the origin, w equals 0. And we'll do another gradient step, back over here. So now you might start realizing that there's a problem. In particular, we're not actually doing anything. And in fact, we're oscillating, we're going to oscillate for infinity and beyond. Okay, so, and and I'll summarize what's happening in a few slides when we compare different step sizes. But the punchline is, the step size is too large. Okay, so let's try a smaller step size. Okay, so now the step size is 0.0001, so 1 over 10,000. Okay, so now we're moving the negative direction of the gradient. All right, because we made a very small update. Good, we actually made progress. We've decreased the objective function. So the y-axis is the objective function. We actually decreased it. So let's do this again. So the slope is, this is the slope. We're moving the negative direction of the gradient. All right, we're making progress. Very slow progress. Takes a really long time. Okay, so maybe this step size is too small. And so if you, plot out a few different step sizes, so the step sizes are on the legend on the right-hand plot, you get stuff that looks like this. Right? So at step size of 0.5, stuff's going up. So I should mention that this is not the exact same learning problem as the previous example. This is based on a higher dimensional problem. And so the actual values of the step sizes are not comparable to the previous example, but the trend is, the qualitative trend is what I want you to focus on in this slide. So, if as the step size decreases, the convergence slows down a lot, right? So for step size of 0.1, we converge very quickly. For a step size of 0.001, we converge very, very slowly. But then if we set the step size too large, we not only don't converge, but we actually diverge. And in fact, in this previous example, if I set eta to be greater than 1, you'll also diverge. Also, keep in mind that the y-axis is not, the absolute values of the y-axis are not meaningful. It's the relative comparisons that's the point of this slide. Okay, so the punchline is we should set the step size as large as possible without diverging. Because the step size determines how aggressively you make an update. But if you make an update that's too aggressive, if you're very comfortable with calculus, you know that what we're doing here is essentially making a locally linear approximation to the loss function. The loss function and so we're making a local linear approximation to the loss function, and then we are basically saying, okay, we'll just make a huge update, potentially huge update in the direction of the steepest descent of this loss function with this locally linear approximation. As you step further and further away from the original point where you made the approximation, the approximation gets worse and worse. So that's essentially what's happening. So you want to make aggressive updates, but if you make too aggressive an update, you don't actually know if you're improving on the original loss function because you are relying on your locally linear approximation at the original point WT. Any questions on that? Yes?
It's like a trial and error, right? You don't know in advance like how large the data would be. So you try different values basically.
A lot of it is going to be trial and error. Certainly, there is theory, and I'll summarize a few of it, suggesting, there's some theory that shows you that, you're guaranteed not to be in this regime where it diverges if you don't set the step size too large. Those theories are bounds, like upper bounds or lower bounds, and so they may not be useful in practice. So for example, the theory says, eta cannot be, if eta is less than 0.001, I can prove that you never diverge. Okay, that's not very useful for this example, but that's something I can prove. Now, that's not to say that these analyses are not interesting, right? The existence of a step size such that you don't diverge is actually already by itself interesting. Like if you're in some really complicated optimization function, you only get one shot, and you need to guarantee you don't diverge, then the theory is actually useful. But in many practical settings, the theory is there's a gap between theory and practice. And that's something that theoreticians are working on, of course. But yes, because of the gap, there's a little bit of trouble. Yes?
Also, you can use adaptive step size. You can monitor the loss function.
Yes, so you can use adaptive step size. And in fact, adaptive step sizes are implemented in machine learning packages such as TensorFlow. And in the latter half of the course, when we move beyond gradient descent and think about more complicated concepts, you'll just be using things like TensorFlow and their adaptive step sizes. That is not going to be the case for homework 1, where you have to basically really understand the nuts and bolts, at least in practice, of gradient descent. So you have to do trial and error on your step size. But in practice, when you actually do machine learning in the real world, and you use these packages, then with these learning algorithms, the fancy learning algorithms have adaptive step sizes, and those will be what you use in practice after homework 1. Yes?
What happens if your loss function is not convex?
That's a great question. I will get to that. Let me think. We certainly will talk about that in week 4 with deep learning. I will touch on it here in this lecture, late a few slides. In machine learning, there's always this lag between, or not always, but there often is a lag between theory and practice. And so theoretically, you might ask yourself, well, okay, the worst case, we can't learn anything. It's non-convex. And what can you do with gradient descent? In practice, we just do gradient descent and its derivative and its variance, and it seems to work really well. So we just live with the fact that they're low quality. Connected to a previous question, sometimes you do random restarts. So maybe if you do maybe you do like 10 different restarts, one of the restarts will get you to a really nice little block. And in practice, that's what people do. Okay. So there's a few other things to keep in mind when thinking about gradient descent. So consider 2 following gradient updates. So we have 2 different loss functions, L and L hat. And L and L hat are basically the exact same loss function. We just happen, L hat is just L times 1,000. So we uniformly scale L by 1,000. Otherwise, it's basically the exact same loss function. They have the exact same minimizers. The exact same W minimizes both. Okay. So if we want the learning algorithm to behave similarly for these 2 loss functions, even though we just scaled one by 1,000, in some sense we want the learning algorithm to sort of behave similarly. What would we do in order to get the learning algorithm, in this case gradient descent, to behave similarly for these 2 loss functions? In particular, how should we tune the step size so that these 2 learning algorithms behave similarly? Yes?
Scale it that way, 1,000.
Yep, correct. We just scale it down by 1,000. Now, this is a very idealized toy example, but it sort of gives you a handle on what we actually care about is the minimizer of this loss, not its absolute value. And so if you have some sort of definition of a loss function that has huge scaling properties, and you have another loss function that is qualitatively similar but has a small scale or a compressed scale, then it gives you, and you want your learning algorithm to behave similarly on both, then one of the knobs you have under your control is, if you have a sense of the dynamic range of this loss function, you can tune your step size so that the learning algorithm, in this case gradient descent, behaves similarly on both. So here's a few rules of thumb. One thing that people often do is they divide the loss function or the gradient or the step size by the number of training examples. So if I have a training set of 1 million or a training set of 100,000, and I want the behavior of the learning algorithm to be similar, subject to the loss function having similar dynamic range, the individual losses having similar dynamic range, then that's just simply normalized by the number of training examples. I noticed that some people are taking notes. That's great. I just, want to emphasize that the slides are available online. If you're the kind of person who wants to take notes just to remember things, that's totally fine. But if you're doing it because you don't realize that the slides are available online, the slides are available online. Okay, so let's talk about adaptive step sizes. Here's kind of a simple trick, a rule of thumb that you can do. There are more advanced things that you can do, not beyond the scope of this class, but the further reading is available on the course website. So we start with a large step size, and if we notice that we're no longer learning with this step size, or we're diverging, we cut the step size down. Let's say divide by 2. And in fact, you can prove that in the infinite, in the infinite limit, the step size must decrease over time to guarantee convergence to the true law. Of course, in practice, we never train for to the infinite limit. We have some budget, and so we don't need to get drive the step size all the way down to 0. But if you're an analysis person, this is what's required. Yes.
Can you explain the first, why?
Yeah. So imagine that I'm a machine learning practitioner, right? And I have 2 customers, and they say, "Can you help me train a machine learning model for these?" Or the same customer gives me 2 training sets, and I want you to give me a version of a learning algorithm so that it works on both of these training sets. And let's say they're both using squared laws, and the radius and the norms of the x's are similar, so everything's sort of similar. It's just that one training set has 100 million examples, and one training set has 1,000 examples. Now, this loss function, as the way I wrote this loss function, it's not always the same for different people. I wrote this loss function as the sum over all training examples. So, if I were just to squint, approximately one loss function is about 1,000 times bigger than the other loss function, just by virtue of having 1,000 times more training data. So that's why. Yes.
So if your loss plateaus, you divide the step size by 2. What if you have oscillating loss? What if you have
Right. So
we had before where you have this oscillating.
So you realize that so we can analyze this specific example because it's super simple, right? It oscillates exactly at 8 = 1. At least if you start at the origin, it oscillates exactly at 8 = 1. If 8 is less than 1, you will. If 8 is less than 1, you will decrease to a point, another point, or you start oscillating. And if 8 is, that's basically how it works, right? And so, in the simple example, if you want to actually converge this to this actual solution, actually converge to it in the limit, you have to decrease your step size over time. So the oscillation, if you're oscillating, if you decrease your step size enough, you'll stop oscillating.
With a more complex function, suppose you get something with 5th order quality instead, you can get more easily track the local minimum.
That's right. Yeah. And deep neural nets are non-convex as well. It's very higher order kinds of shapes of the loss function, and people just sort of accept it. Okay, so let's talk about convexity. So probably, I'm gathering that many of you are here already know about the concept of convexity, but in case you don't, just want to touch on it. Convexity is a function is convex if you take any 2 points of that function and you interpolate between it linearly, that interpolation sits above the original function. So what that means is I take these 2 points, right here and right here, and I do a linear interpolation between those 2 points, and that linear interpolation sits above the actual function. There's a few other conditions that need to be met, but that's the high-level bit that's relevant. It has to be over. It also has to be over a convex set and stuff, but it's not really important for machine learning purposes. So So this function, this blue line, is not convex. So if I were to interpolate between 2 points, there are cases where the interpolation sits below the function. For a convex function, the interpolation always sits above the function. For convex functions, it is easy to find the global optimum solution. In fact, you can find it for nice, well-behaved convex functions. You can find it easily using gradient descent. A function is considered strictly convex if the interpolation, if the interior of the interpolation is always strictly greater than the actual function. Another way of writing convexity is the following form. So for any 2 points, x1 and x2, x2 is always greater than or equal to x1, and it's locally linear extrapolate. It's locally linear surface. Right. So basically, this basically describes this blue line here, right here, and so what it's basically saying is that the tangent line, or the tangent plane, or the gradient plane, if you will, around any point sits below the function. That's another definition of convexity. They're equivalent. You can prove that they're equivalent. So whenever we do gradient descent, we have a locally linear approximation of a function that we were minimizing that is always an under approximation of the original function. Function is always above the local linear extrapolation. And there's so all local optima are global optima and convex functions. So this is also a convex function. It's not strictly convex because this basin down here is exactly a linear function, so it's not strictly convex. Actually, it's not strictly convex for multiple reasons. A strictly convex function is a unique global optima. So all of these are local optima for this guy, and they're all also global optima. Almost all standard learning objectives are strictly convex. Squared loss, SVM loss, and a few of the losses that we'll see next week. Deep learning is non-convex, not because of the loss function, but because of the function class. It's not a linear function class. But the loss function, for example, if you do deep learning for minimizing squared loss, the loss function itself is convex, but the overall objective is not, because the function class itself is not linear. And yeah, we'll talk more about deep learning in week 4. Okay, so I just want to touch a little bit about what you can say theoretically for learning gradient descent style learning in these kind of learning objectives. So if the learning objective is convex, which it is for squared loss and linear functions, then we can reason about how many iterations we need to converge to the global optimum, or be within epsilon to the global optimum. And so if you can bound something of what's called the Lipschitz property of the function, which basically bounds how big the gradients can be, then the convergence is 1 over epsilon squared. So if we want to get more and more accurate, we need quadratically more iterations of gradient descent to converge the solution. If the gradient itself is differentiable, well, Lipschitz, but you can think of it as differentiable. So therefore, it has second order gradient, second order derivatives. Then it's 1 over epsilon. So as we increase the precision of how close we want to get to the true optimal, well, the number of iterations of gradient descent only increases linearly rather than quadratically. And then if the objective function is strongly convex, which basically means it looks something like a quadratic function, so it has a really strong curvature, then it only takes log of 1 over epsilon iterations to converge to the global optimum with an epsilon. And if you're interested in this style of analysis, this is beyond the scope of this class, to go into these things in depth, you can look at one of the free online textbooks linked to from the course website. So, as I talked before, in general, if you actually want to truly reach the actual global optimum exactly, it takes infinite time in general. But machine learning is used in practice not because you can exactly learn everything perfectly, but you learn it good enough to be useful. So, what we really care about is not reaching the exact zero loss in the infinite limit. Well, we want to know that we're in the regime where we've basically converged to something really good. We're within a small epsilon of the global optimal. And so, how do we know that we're here and not here, right? If we don't know what W star is, how do we know that we're in the regime down here and not in the regime up here? In some sense, that's all we care about in order to use machine learning in practice. So, the stopping condition. All those convergence analyses, they're just worst case bounds. Sometimes they might say something that you would never do in practice, like, oh, you want to be within 1% of optimal, you need, a billion iterations to guarantee that you're within 1% of optimal. Okay, in the worst case, that might be true, but what about in my specific instance of a learning problem? Do I really want to rely on theory exactly? Again, because there's a gap between the theory and practice, there's a little bit of trial and error that needs to happen. And of course, if you're interested in machine learning research, because there's a gap between theory and practice, there's always an opportunity to do interesting machine learning research. Okay, so one way that we can do this is to stop when progress is sufficiently small. So, if every once in a while we look at the reduction in error and the relative reduction is less than some threshold, let's say less than 0.1%, then we just stop. We stop after a pre-specified number of iterations. So after 10,000 iterations or 100,000 iterations, we stop. We stop when the validation error stops going down. So again, we can have a training set and a validation set. In fact, you probably always want to have that. And when the validation error stops going down, either we're close to converging or we're close to starting to overfit. Either way, we should stop. So you notice here that there's an entanglement of whether or not our learning algorithm is converging versus, are we going to start overfitting or not? And in fact, in deep learning, this question is quite complicated, and it's the topic of current research. Okay, now let's talk about a limitation gradient descent. So in practice, no one actually uses gradient descent. Although, we use gradient descent like algorithms. And the biggest reason that no one uses gradient descent in practice is that making a gradient update requires a full pass over the training data. If my training data has 1 million examples, that means I have to loop over all 1 million examples before I can do an update of my model. That is simply too slow in most applications. In other words, I have to do this summation, right? Because it's for loop over my training examples. And if capital N is huge, this is quite slow. Especially if your step size is really small. So very expensive if the training set is huge, which it typically is in practice. So the question, the obvious question we can ask is, well, do we actually need to do a full pass over the training data? And that's where stochastic gradient descent comes in. Stochastic gradient descent is actually the backbone workhorse learning algorithm that is used in basically all modern machine learning packages, stochastic gradient descent and its more advanced variants. Okay, let's suppose that the loss function decomposes additively, which it does here. So here I'm just going to normalize everything by the number of training examples. Nothing else changes, right? And then I'm just going to say, I'm going to say that the loss function is the average over a bunch of other smaller loss functions indexed by little I. In this simple example, little I corresponds to the individual data points. This is the loss on a specific data point. So it's the exact. I've done nothing other than just simply rewrite things in a slightly different notation. But now, now I can view this as the expectation, right? So the loss function over my overall training data is simply the expected loss over these little additive loss functions that are added together, and each of those corresponds to a single training example. Okay, by linearity of differentiation, the gradient of the original total loss function is equal to the gradient of the expected loss, is equal to the expectation of the gradient of the individual losses. So that is one of the, so there are many motivations for stochastic gradient descent. It's a very fundamental algorithm. You can analyze and improve it and derive it from multiple motivations. I just gave you one motivation. Here's the motive. So the reason why people do stochastic gradient descent is that it suffices to take a random gradient update, as long as it matches the true gradient in expectation. So at every iteration t, if our loss function decomposes additively, we treat it as this expectation. We sample one of the losses from our set of distribution of losses at random, and we do a gradient update. And the expected value of this gradient update is the gradient update of the original loss function, the total loss function. That, in a nutshell, is stochastic gradient descent. And if you actually think about it, stochastic gradient descent is an online learning algorithm. We're giving it a stream of data. We have this learning algorithm that's being fed a stream of data and making small updates as it's being fed this stream of data. Okay, in practice, things are a little bit more complicated. People don't do singleton stochastic gradient descent. People often do what's called mini-batch stochastic gradient descent, where each else of I is a small batch of the training examples. For example, each else of I corresponds to 500 examples or something like that. There are a few reasons why people do this. First of all, in modern computing architectures, you can leverage vector value operations by going over batches of 500 or so at a time rather than a single example at a time. It's just better in terms of computation and memory access. Another reason why people do this is that it decreases the volatility of the gradient updates, right? So even though in expectation the gradient updates match the gradient of the total loss function, if you only sample one point at a time, the randomness can be quite high. And so if you instead sample about 500 at a time, the stochasticity or the volatility is lower. So there are many reasons why people do this. And in fact, mini-batch SGD and its derivatives, such as those based on adaptive step sizes, is the industry state of the art, or the de facto standard. If you are implementing, if you run TensorFlow with a deep neural net, you tell it to run a learning algorithm. The learning algorithm that's the default one is some variant of mini-batch SGD. Okay, so now let's talk again about checking for convergence. So how do we check for convergence? Well, do we want to evaluate the loss function of the entire training set at every time? So here's a thought experiment. I loop through, I have a training set of, let's say, 1 billion examples, and I loop through 500. I look at 500 of them. I do a gradient update, and then I look at the remaining 1 billion examples, see if I've converged. That seems kind of silly in terms of computation. So in practice, when people do stochastic gradient descent, you don't check for convergence after every iteration. Right? You don't write this for loop over your validation set saying, have I converged, yes or no, after every iteration. People do things differently. Some people check every 1,000 iterations. Some people check every 1 million iterations. This is like a flag you can set in your machine learning toolkits. You may also just decide to evaluate loss on a subset of the training data, not on the whole training data. Just check it every once in a while. This is more. This issue has more to do with simply just system design than the fundamental mathematics. Okay, so just to recap, stochastic gradient descent conceptually decomposes the loss function additively, and then it chooses a component, one of the additive components of the loss function randomly, and makes a gradient update based on that, just evaluating the gradient on that one component. The benefits is that it avoids iterating through the entire training set for every update, and that you can show all the convergence guarantees of gradient descent, by and large, also hold for stochastic gradient descent. They're a little bit slower because things are an expectation, rather than because the gradient is a stochastic gradient that it has the same expected value. So things are a little bit slower in terms of number of iterations, but of course each iteration is so much faster, and it's the industry standard. Okay, so I want to come back to the. Oh, by the way, are there any questions on stochastic gradient descent? Yes.
So if people pick like 500 to 1,000 at a time and iterate those randomly, if you have a billion components, aren't we kind of implicitly assuming that most of those components were close to optimum anyway, if it doesn't take a long time? If we're only updating, say, 500 to 1,000 at a time, and we have a very large number of examples.
Well, we'll eventually touch every training example, so I'm not sure I understand your question.
Well, it depends. If your starting point is here and your optimum is way over here, and you've got this is a billion-dimensional system, and you're moving, so yeah, you might hit every point in your system eventually. But if each point is far away, each point needs to be hit many times in order to get to the optimum. So is it kind of like, do you kind of make the implicit assumption that like your starting point is close enough that you can do that, and you don't have to hit every point a lot?
No, I think the idea is that one of the reasons why stochastic descent works is the idea that there's redundancy in your data. So like, for example, if I'm training an image classifier, and let's take ImageNet, 1.4 billion training examples, images. About 100,000 of those are images of dogs, and they're not that different from each other. So the reason why, one of the reasons why in practice we believe that you have reason to believe this stochastic descent can work well is that there's a lot of redundancy in your data. So if I just do a random sample, of course it's not exactly representative of the overall data set, but it's not like each data point is so unique from each other data point.
Yeah.
Okay. Any other questions on that about SGD? Yes.
So is there a principal way to choose like your batch size?
So it turns out that one of the dominating factors of batch size is your computer architecture. So if you've taken computer systems, you know that if you just go a little bit over the memory or some hard threshold of your system, things get twice as slow for not much more benefit. So depending on your architecture, you may be able to afford more. You should certainly, because if you have an architecture that can support doing, if you have a GPU, right, that can support doing like computing 1,000 gradients of 1,000 examples in parallel for the same speed as computing one, then you just set the batch size to 1,000. So I would say the dominant factor is actually the computer architecture. Because here's another thought experiment. Suppose I had a computer architecture that was massively parallel. I can compute 1,000. I can compute 1 billion gradients in parallel. Well, gradient descent in terms of number of iterations converges faster than stochastic gradient descent. The reason we use stochastic gradient descent is that if you multiply the number of iterations to converge plus times the cost of convergence, it's faster than gradient descent. But if I have a massively parallel processor that can actually compute a billion gradients in parallel, I'll just do gradient descent.
Doesn't that the stochasticity of stochastic sometimes help?
That's a great question. Does the stochasticity of stochastic gradient sometimes help? And the answer appears to be yes for deep learning, although people don't exactly understand why. And that's actually a topic of current research. It turns out that stochasticity actually somehow helps prevent the neural net from overfitting. It's been empirically observed. No one fully understands it completely. But in the case of convex loss functions and linear function classes, which is what we're looking at right now in this class, and in terms of the purely optimization standpoint, we have this learning objective on the training set. Let's just optimize it, ignoring the overfitting scenario. If I can afford to do gradient descent, because I have a massively parallel computer that can hold that can do a billion gradient operations in parallel, there is no reason to do stochastic gradient descent from a purely optimization point. The reason we do it is because if you multiply the cost of each iteration times the number of iterations, stochastic gradient descent is much faster.
Is it possible that a specifically designed stochastic predicate, a specifically designed set or a sequence of example will ruin the whole network?
Yes, that's why people typically loop through the data set at random. So you randomize
the randomness be like everything.
The randomness typically, you avoid these crazy situations or some of these crazy situations. Deep learning is not well understood theoretically, so at some point you're going to ask me questions where I will just keep saying I don't know. One of the reasons, but yes, you typically want to randomize the training set before you move through it to avoid some sort of kind of artifacts that could be avoided if you randomize. Okay, in the final few minutes, I just want to revisit the perceptron algorithm. So this is the algorithm. I simply presented the algorithm without telling you what objective function its algorithm is. And I just want to come back to this. So this is the objective function that the perceptron algorithm is implicitly optimizing. So the perceptron algorithm was presented without an objective. It was actually, so Rosenblatt was actually a computational neuroscientist. He was thinking about how biological neural nets learn. And so his algorithm, also known as, it's basically, the perceptron algorithm is basically a precursor to the backpropagation algorithm.
Yep.
Is you can actually sort of reanalyze it from a modern perspective and say, okay, this is the actual learning objective that the perceptron algorithm is optimizing. And so here's the loss function. The loss function is 0 if we make a correct classification, and a linear function if we make an incorrect classification, and the cost grows linearly with respect to how far we are from the hyperlink. That's the loss function. And if you think about the gradient, right? So over here, we're making a correct prediction, and the gradient is 0. So we don't do any updates. Over here, we make a misclassification, and the gradient is gradient is linear. We make a linear step in the direction towards 0 loss. So we can actually revisit the perceptron algorithm, which was proposed by people from a computational neuroscience perspective, and reanalyze it, or at least reconsider it from the perspective of modern machine learning. Okay, so here's the more complete pipeline. Training data, model class, loss function, optimizes loss function with cross-validation, using stochastic gradient descent. So we just added this little term here to this complete pipeline after lecture 2. And that's it. Okay, next week we're going to look at different loss functions. We'll start to look at nonlinear bonus class, so we'll look at and recitation tonight.